Just to go back, the universe can be described statistically as homogeneous and isotropic, but as I hope I showed you yesterday, there are a lot of voids and halos that forms in the universe. And so the question is, can we still treat this system as being a pure Friedman-Lemaitre Robinson-Walker background, homogeneous and isotropic? The answer is either yes or no. The cosmological field that tries to answer this question is called cosmological back reaction. And we identify basically two different scenarios, one in which, on average, this looks like slightly different than Friedman-Robinson-Walker, or this is actually statistically a good approximation, Friedman-Robinson-Walker, but since we live in some different inhomogeneous region, what we observe in our light cone is has some modification with respect to the background evolution. So these are kind of the two situations, and either classified as strong back reaction or weak back reaction. Now, how do we deal with this type of problems in practical mathematical way? Well, we use the so-called Bucher formalism. And it assumes, essentially, that the space-time can be foliated into space-like hypersurfaces. So I don't know if any of you is familiar with the ADM formalism of Einstein field equation. Essentially, you can always choose coordinates, let's say, in which you can write your matrix as ds squared is equal to minus dt squared, some function of time, plus some shift function in I dx I dt, plus some h ij spatial part dxi dxj. So, and you have your spatial three-dimensional metric, some lapse function that is some sort of cosmic time parameter, and some shift that describes off-diagonal terms, so basically rotations. And this basically is completely equivalent to choose a foliation of space-like hypersurfaces. These are the space-like hypersurfaces, three-dimensional spatial ones, and a shift parameter that, a lapse parameter that evolves these space-like hypersurfaces in time. And this N, as again, describes some sort of inhomogeneous time-space component. So if you start with this sort of ADN decomposition, then you can always, at least in cosmological scale, say, okay, this is probably not existing because essentially vorticity on large scale is not being sourced by nothing, so we usually kill these off-diagonal terms, and we are left with some space-time part and some time part. So this really becomes a sort of cosmic time, if you want. If you have questions, as usual, please stop me and ask. It's called ADM decomposition from Arnold, Deser, and I don't remember. Excuse me? Misner, of course, Misner. Thank you. Mr. Mass and all the stuff. Okay. This is very useful to study general relativity in the Hamiltonian formalism, in which you basically promote these variables here to generalize coordinates and generalize momenta taken as the derivative of those. It's also very helpful in numerical relativity, because basically you evolve your grid by saying that every cell in the grid has a ADM-like structure. So you impose boundary conditions between cells and do all the black magic. So it's a very helpful decomposition. Okay, but for our purposes, basically, once we have this decomposition that describes, again, a supposedly inhomogeneous and anisotropic space-time, you can attempt to write down it in terms of averaged quantities. What does it mean? Well, let's suppose that we have this non-spherical volume with some anisotropic expansion rate that I will call h of x and t. A very useful way to deal with this problem is to define an average scale factor. So basically a radius, an effective radius, such that you basically map this object into a sphere with a certain radii r, which will be your average scale factor. Let's call it for a second AD. So this is the dominion D. This is its spherical equivalent. And then you can define the expansion rate of the average, so some sort of A dot D divided by AD, like if it was an Hubble factor. And this is usually called theta. And then you can write your H as some object theta, plus the deviation from isotropy and homogeneity, which are usually characterized in terms of a shear tensor called sigma sigma beta, plus some vorticity tensor, which again is AB, WAB. Thank you very much. So the idea is I have a problem which is very weird and complicated. I convert it into a problem for something like the average expansion rate of that volume, because I kind of coarse grain this complicated inhomogeneity. And my average expansion rate, like my real expansion rate, is going to be something like a combination of the average plus vorticity terms, or shear anisotropic stress. So basically, let's say this part here describes how much this domain is twisting on itself or spinning, and this sigma describes how far away from isotropy is. This has been done a lot in this ADM formalism, for example, to study Bianchi cosmologies, which are homogeneous but anisotropic spacetimes. And in the so-called ADM variables, which ADM from before, you basically end up having something like your average radius written in terms of e to the omega. So let me make it a bit clearer. This is just to give you a little practical example of how this stuff comes out. Bianchi spacetime, let's take Bianchi 1, which is the simplest one. It's a flat anisotropic but homogeneous universe. It has a metric which is of the type dt squared plus a squared dx squared plus b squared dy squared plus c squared dz squared, where a, b, and c are functions of time. In particular, in vacuum, so r equals 0, the solution for this matrix is t to the p1, b t to the p2, c t to the v3, and there is a certain relationship between p1, p2, and p3, and p1 squared plus p3 squared is equal to 1. And this is called Kastner solution. So this is not really important, it's just to say, let's take an example of an isotropic spacetime, which is homogeneous. This describes something that on each spatial direction is expanding at a different rate. In particular, because of these two constraints, one of them will be shrinking and two will be expanding, or the other way around, because you cannot have both of these true if they are all positive. So a useful way is to define an average scale factor, which is going to be something like the of ABC, and you call this object a to the omega, and then a, b, and c will all be written in the terms of this ADM variable, which by memory will look like something a is equal to e to the omega. Let me do it this way. B, C. They all will be something like the average plus B1 plus B2 plus B1 minus B2 minus 2B1. And so you can clearly see that the product ABC will be your e to the 3 omega, so the volume, and the anisotropy is fully described by this quantity beta 1 and beta 2. Yes. So this decomposition is helpful also when you don't have this nice Kastner solution. It's true for all the Bianchi cosmologies. There are 9 different spacetimes. So clearly this is an overkill. It's killing a mosquito with a gun for the Kastner spacetime where you have this explicit solution. But this is just to show how these Misner variables come up. And if you write down the Einstein equations, the zero equation for this particular variable will look something like omega dot square is equal to 8p g rho, so your dust field, plus beta 1 dot square plus beta dot 2 squared. There will be some coefficient in front of beta 1 and beta 2 that I don't remember. But this is exactly what I was telling you about before. You have your theta square, theta dot square, your average expansion rate, which will be given by the average density, plus some sigma ij, which in this particular case takes just the form of beta 1 and beta dot square.
Yes, diagonalize the kinetic term.
Exactly. Precisely. Everyone is happy with that? Okay. So the idea is that taking averages, we smooth out the coarse grain of anisotropies and inhomogeneities. But then we are left with a problem, which is what are the physical quantities we are observing. In other words, let's suppose, for example, we were talking about the expansion rate. Well, we have an effective radius that we have called AD. What is its expansion rate averaged over some volume? So to make it a bit clearer, we have an observable or a cosmological quantity A that we want to define. And then, rather than observing A, we observe its average over a certain volume, for example, the density. Now, we need a prescription to take these averages. Boucher formalism, or Boucher's quartet, is exactly a way of doing this procedure. And the prescription that he gives is to compute this average, take the integral over the space-like hypersurface that I was talking about before. So these are Gaussian normal coordinates on that space-like hypersurface of the quantity A multiplied by the square root of minus g and divide by just the volume. And this is the volume D. It's the spatial part. It's the, sorry. Yeah, let's put me just H and H. Thank you. The induced spatial metric on that free surface. So Boucher said what we can actually measure is this object, so the average of the quantity, because we don't have access to the full space-time. And then you realize that there is one problem. The time derivative of the average is different from the average of the time derivative. Does this make sense? Because if this is a function of time and this is a function of time, when you take the derivative, you have some non-commutativity going on. So let's try to find out this non-commutativity, and let's take the time derivative of this object. Let me call these, in a very improper way, V, volume. Then the time derivative of AD is going to be something like minus b dot divided by v, the derivative of the fraction, times, let's call this, well, I will write it for a second, just square root of h a divided by b. So this is again the average of a. And now we have the other term, which is the derivative of this one, which contains two terms. One is the integral, the cube x of a dot, square root of h, and the other one is the integral of a square root of h divided by v. Now, on this hypersurface, as I mentioned before, we kind of define an average radii. So this, essentially, you can imagine it as, if it was Friedmann-Robinson-Walker, you will have a squared, the square root of a squared will be a. So here we have the average scale factor in this averaged volume. And so this just becomes minus b dot divided by v a plus the average of a dot, because the derivative entered here, times h, plus we will write this as h dot divided by h times square root of h. And so this is just the average of a times theta, because we are taking the derivative of this and divide by square root of h, which is your average expansion rate. So we have this, if you want, nice formula in which the time derivative of an observable average is equal to minus theta a plus a dot plus the average of a theta. And this is called the non-commutativity relation of Bucher formulas. What I'm trying to say at the end of the day, that since this object and this object are not the same, you can have something, you can define, basically, something like this object. Let's call it x for a second. It will change name in a second. Let's call it q to make it clearer, which is essentially the variance on your time derivatives of the observable a. Why is this important? Well, because it turns out that in terms of this average scale factor, you can write down the analogous of the Friedmann equations, which makes sense, right? Because I'm averaging, so the average must look something like Friedmann, where now we have the average density rho, cosmological constant, the average spatial curvature r, and this q. This q, again, is defined as the variance in the expansion rate. So something like this. So essentially, everything that happened is that for your average volume, you still have Friedmann-Robinson-Walker plus some additional terms that are due to the spatial curvature of the thing, and the variance in the expansion rate. So this thing is just a spatial curvature, but I copied the formula from two different books, papers, sorry. Actually, no, I'm sorry. This is actually the vorticity term. So it will be the omega b, but we are considering irrotational stuff, so it's there. Apologize. I lied. So neglect this term. So again, let's look at the right side. You have this cosmological volume, and you have a cluster here, and a void here. this is contracting, and this is expanding with respect to the background FLRW, let's say. The fact that there is a variance in the expansion rate between these two objects, when you take cosmological observation over this volume, gives you an additional term in your Friedmann equation, which is the variance in the expansion rate. Perfect. Now, all this formalism was suggested and has been tried to use to explain dark energy. Because if you, for a second, neglect this lambda here and only look at Q, or the spatial curvature, you would say maybe this can be dark energy on reasonably small volumes. And that's why Back reaction was popular a few years ago. I should add that in a Newtonian context, there is no spatial curvature, because Newtonian gravity has no spatial curvature. And this Q is completely described by peculiar velocities. So just in Newtonian cosmology, basically a velocity v and an expansion rate are the same thing. And so you can write this Q as proportional to the peculiar velocities in your local region. And since peculiar velocities in cosmology are of the order, contribute terms of the order Vp over c, and this is 10 to the minus 3, and this is squared, it means that your Q in Newtonian framework is of order 10 to the minus 6. And that was considered a proof of the fact that back reaction cannot be dark energy, because this is a ridiculously small term. Again, the trick is this Newtonian framework here. If you have spatial curvature, as you can see, Q and R are deeply interconnected. Okay. Also, we can immediately recover the Friedmann limit in the sense that in Friedmann-Robinson-Walker, let's say curved Friedmann, you have your K. So your three-dimensional curvature is just K divided by A squared, with K equal plus 1, minus 1, or 0. And so your Q is equal to 0 because there is no variance. So this term is 0, and you get basically the time derivative of a constant plus d is equal to 0, and this is clearly constant. So it recovers the Friedmann result. Okay, now I will talk a bit about my work, because on this subject I have very recently wrote a paper. I wrote it in collaboration with Ryan Camilleri, which is a student, a PhD student at UQ, and Rodrigo, which is a professor at UFBA. Yeah, it's a beautiful paper, you should read it. What have we done? Basically, we decomposed the Friedmann equation by saying that the total density is the composition of some voids and clustering regions. And we stole the formalism of coupled dark matter, dark energy, and introduced a coupling between the dust fluid and the voids and the cluster. So essentially, we have three fluids, dust, voids, and clusters, each with a different equation of state. Dust has no equation of state, has no pressure, so W dust equals 0, but voids and clustering region have some W. And the coupling is such that the total matter is conserved here. Okay, so what have we done is essentially to use.
Sorry, can you just clarify a little bit better why pretty fluid description could describe the physics? Naively, it looks very different from pretty fluid, no? Having something that collapses here, something that expands there, it doesn't look like at all. Like,
I agree. But if then you start to have a lot of clusters and a lot of voids all aware over your volume, on average, this will look like two fluid of non-interacting particles. On a very brutal average, I do agree. But essentially, this is really an attempt to say. I also will add something very soon, but this is a brutal attempt to say, we know that this happens, that structure forms. And we know that this structure formed out of something that earlier was dust, and now it's something that we cannot describe fully, because we don't have a general relativistic description of a metric with clusters and voids matched together. So at this level, I'm doing absolutely nothing wrong. I'm saying this fluid, if they happen to exist, will be coupled this way. And if there is absolutely no difference between those and dust, I will just have a 0 here and a 0 here. Yes, it's just the voids and the void region and collapsing region. I'm treating all the collapsing region in the universe as a fluid and all the void region in the universe as a fluid. In the universe. I can compute it from first principles in a second. Yeah. At this moment, I'm just setting up the equation and saying that these voids and clusters do not come out of nowhere. They are taken from the dust. So there is a loss of energy in the dust fluid that is converted into these fluids. So
Because it seems like you have like some kind of interaction between voids and clusters.
you do describe exactly by this coupling term here.
So the point is phenomenological.
It is purely phenomenological, all the model. And I will go back in a second why I don't really care about perturbation. But like for the moment, I'm just setting the background equation saying dust at some point in late times become large-scale structures, which are more complicated than just dust. And I distinguish between two types of components in the large-scale structure, expanding region and contracting regions. And I say they might have a pressure, contrary to dust, which is a free parameter at this moment, V. And also the B and the C are coupling terms. Now, as I showed you yesterday, with pressure that I can compute how much collapsing region and how much expanding region I have in lambda CDM using the pressure formalism and generalization to void. So now I make an ansatz on the amount of dust and the amount of voids, which is just out of the total is 1 minus the amount of voiding region and collapsing region. To define this fraction, Fc and Fb, I use pressure by saying now one specific thing. I know exactly for this reason here that virialized regions, virialized objects, do not contribute any back reaction. So there is no difference between a dust particle and a virialized collapsed object. So I don't want those pressure collapsed object to be part of my back reaction contribution. And so I just decide that if there is any back reaction at all, it must come from those objects that are collapsing non-linearly but not virialized. Also for the clusters. Also for the voids. So I'm taking voids and clusters that are expanding non-linearly. And I just compute them as the amount of objects or regions in the universe that have surpassed the threshold for turnaround. So for example, for collapsing objects, they begin to collapse, but are not virialized yet. So this fluid is very transient. It does not exist all the time. It exists as long as these objects are forming. If structure formation is suppressed, all the objects collapse to virialized, and there's nothing left. So this is just a fundamental ansatz to get the F, or so the fraction of elements. Just to show what I said before, you can map this model, of course, to some Buchert average formalism by matching the kinetic back reaction term with this term and the spatial curvature with this term. So in some sense, what I'm really trying to doing is to say, I have observation on a cosmological volume where there is the cosmic web. I smooth out and describe it as a Friedman universe with some additional contribution coming from collapsing and expanding region. Somehow, I am trying to give, through these coupling terms V and these Ws, a prescription to perform these averages. So, okay, the formalism is not new. It's stolen from interacting dark matter and dark energy, which is very known in the literature. As you were mentioning before, how do I set the adiabatic condition? I just set the coupling term in the perturbation equation this way, which is the same stuff that is usually done in interacting dark matter, dark energy. And if you were wondering how much of these objects there are around in the universe, this is a plot to show it. Dashed lines are redshift 0.5, continuous one is redshift 0. So the green line is the number of objects that have passed on around. The orange line is the number of objects which have virialized. The difference between the two is the blue line, and is my f of c, which, as you can see, has a very defined maximum, and then at some point in the future will go going to 0. And the same for the voids. So see, this is the fraction of rho dot, or the volume, contained in non-linearly expanding or contracting regions. Now, it's important that this depends on the scale R, because as I showed you yesterday, Prescherter depends on this R here, the variance on a sphere of which radii. So this depends on the scale of the voids and the scale of the cluster, or the other way around. Why this is important? Because I really have no idea of which scale is relevant for back reaction or not. Like, in this cosmological volume, is an object non-linearly collapsing or expanding of these sides relevant for back reaction? Or only these objects are relevant? I don't know. And that's why this R is a free parameter. This is just saying the number of collapsing region of 10 megaparsec that there are at redshift 0 with respect of the total volume. And you see it's an infinite, like a very small fraction. These are objects of 1 megaparsec, and they occupy 0.2% of your volume. Sorry, 20% of your volume. So I use an ansatz to find what Q is. What about W dots? Now, this is the other ansatz, and I'm saying that differently to dust, this region has some internal energy. And since those are spherical regions that are either collapsing or contracting, I associate this internal energy with their spatial curvature. But at this point, imagine I don't know even what is it. I'm just saying that there is some internal energy. And then the pressure is just given by the time derivative of the energy with respect to the volume. Like, this is thermodynamics. Now, I know this formula because I showed it to you yesterday, where I associate the curvature of a region which is with its initial density and radii. So I compute the internal energies as basically this spatial curvature here. I plug them into this EI, and so I sum over all the internal energy of all the objects of a given radius. And this sum becomes an integral in R. So this is where the free parameters come in. This is the minimum radii of clusters relevant for back reaction, and this is the minimum radii of voids relevant for back reaction. Free parameters. So if the universe is really, if there is no back reaction at all, and I try to fit these things with data, I should get an RC and RV, which are very large, and so they don't occupy any fraction of the volume, and there is no back reaction. This is what I've done. We fit those RC and RV using real data. These are DESI R5 supernova. These are the orange line are DESI BAO, and the black line are F sigma 8 measurement at low redshift from SDS. And so this is the size of the clusters, and this is the size of the void, starting from Planck initial conditions. So this is a universe that starts with Planck best fit, lambda CDM, and then later on in the universe it becomes something else because of this back reaction. And these are the constraints we get. Interestingly, this green box here is a region of the parameter space where both the H0 tension and sigma 8 tension are alleviated, or if not solved at all. So Desier 5 is just a fit of distances to the supernova because they're supernovae. BAO is BAO distance, and SDSS is F sigma 8. This is the first two are background, and this is a perturbation. Sorry? Of F, which is d prime over d. So basically, in this model, I actually did in the sense that, sorry, I didn't put the slide, but basically I'm saying that dust is still collapsing and getting nonlinear, whereas the voids and the cluster are just transient objects which do not have perturbation. So the actual equation delta dot dot plus q h delta minus 4 p g rho delta, I'm putting here rho dust because it's the one that is actually collapsing into some object. And so the evolution of perturbation is changed with respect to the standard Friedman because this is different and this is different.
So in there, I would assume that you will have some coupling term. Instead of C, you will have like, as you had it before, something is B and C that were telling you the perturbability.
Not really, yeah, not really, because if you use this coupling term here in perturbations, it disappears for the specific form of Q. It's almost a miracle, but I computed Q out of first principles, and then I turned it out to be 0, this term. I mean, the Hubble rate changes at late times in this cosmological volume following this basically plot. If you have, like, let's say that I trust this specific best fit from the Desier-5 supernova, I will get a certain value for C and RV, which falls basically here. And so the Hubble rate in this model is slightly lower than lambda CDM, or than the Planck best fit value, or slightly larger if they fall in this region. They are of the cosmological volume where you're performing the measurement. No. It's the free parameter of the model. Like, the question is, what is really, I will put it, I have a certain cosmological volume with nonlinearities, and I ask, what is the minimum size of collapsing region or expanding region that is relevant for back reaction? And this depends on the size of the volume. RC and RV, I'm constraining it with data. These are the constraints. Like, this is really constrained using Desier-5, BAO, and SDSS. So I have another slide here in which I can show how the field look like. This is FS8 measurement. And if you take the best fit line to this data for our model, is this yellow thing here. And the green one was the region of overlap here. So for these values of clusters and RC and RV. And it's a better fit than Planck lambda CDM. And this is how BAO data change with respect to lambda CDM. So the dashed line The dotted line is the DAISY-BAO best fit, lambda CDM. The dashed one is the DAISY-BAO, so Planck best fit. And this continuous line is our model. Mm-hmm. Yes, for D, and I will tell you how D changes with time. This is a plot of distances. These are the distance to the BAO measurement at redshift 0.5 and the others. So this is a actual co-moving distance, dm, and dh is just an expansion history measurement because dh is basically Cz divided by h of z. So the integral of these is proportional to the distance. So these are if you look at this best fit region here, it basically is telling you that clusters needs to be very large as preferred by the data. And so there will be no back reaction from collapsing objects, or collapsing objects are not relevant for back reaction. And it's all coming from voids of this region in this cosmological volume. No, exactly. But again, the point is, if there is no back reaction at all, this model, and lambda CDM is the best model, I should see all this plot here in the top right. Because for these values of RC and RB, there's basically no region. Top right. Very large, meaning very large voids and very large cluster. Because basically say, what are the objects relevant for back reaction in this volume? These type of voids and this type of clusters. How many of them there are? 0. Or 1 or 0, because maybe there is no collapsing region as large as this one. If this is basically, this would be an expanding region of 15 megaparsec, and we know that there are 0 on this cosmological volume. Sorry, a collapsing region of 15 megaparsec. No, sorry, more, because it's logarithm of that. I mean, large objects. Yeah. Okay, so I used a lot of time here, so now I have to run. But this was just to give you an example of back reaction model that is quite recent, and it's from me. And this is how I'm hoping to try to use data to actually fit these back reaction models rather than, just give a mathematical prescription for how to perform averages. Now let's go for the last 15 minutes to something that is really the state of the literature about metric of the local universe. In theory, we have basically 2 approaches. One is cosmography, which is model independent, and the other one is to use analytic solutions of general relativity to try to study this type of effects. So cosmography, this is the definition that Weinberg gives. For sake of time, I'm going to skip it, but it's in the Bible of general relativity. It was born basically in the early 2000s as a way of doing distance measurement, assuming FLRW, but no hypothesis on the energy content of the universe. So basically, you can imagine this approach as being just a Taylor expansion of the luminosity distance. So you have your DL, and you expand it in terms of linear term plus some alpha c zeta squared, and so on. Turns out that essentially you just need 3 parameters, which are h naught, j, and q, which are called deceleration, jerk, and Hubble constant. So this is basically a Taylor expansion. And this is what Q, J, and S look like. S is the snap, and it's the 4th order. I didn't even put it here. And this is how the Taylor expansion goes if you do it fully for the luminosity distance. So as you can see, the S term enters only the cube terms, so it's usually completely ignored. Now, there is a way of doing the same kind of Taylor expansion for average scalar quantities, so kind of resembling the theta average expansion rate I was telling you about, and then expressing the luminosity distance as a function of these. And it turns out that you can define similar objects, which are the Gothic Q, Gothic R, and Gothic J. This formalism is fully model independent. It only assumes that the Etherington relationship between luminosity and angular diameter distance hold. So basically, this is true in any metric theory of gravity, even if it's not FLRW. Or it can be F of R, it can be whatever. It's a kinematical decomposition of average scalar quantities. And it has been developed fully by Asta, which is now a professor in Copenhagen, but this is part of this work comes actually from her PhD, so it's very impressive work for a PhD student. I was very envious because I myself was a PhD at the time. As you can see, H basically became this T that I was talking about, plus some shear quantity and some for acceleration, depending on your basically local dipole. And at the end of the day, you get an expression for the luminosity distance that looks like this one. But rather than having 3 parameters, now you have 9 for the linear order, which are monopole, quadrupole, octupole of the 0, 25 for the z squared, and 61 for the z cube. So if you do the math, this is a lot of degrees of freedom. Yes. I actually am sure that I had a simple explanation for that. It's not coming to my mind, but it's related to the amount of actual degrees of freedom that you can have in this expansion when you go on it. So this is a monopole term, but it's not. No, each of them can have monopole, dipole, quadrupole, octupole, because each of them is then expanded in multiples. That is monopole plus the dipole plus the quadrupole. Yeah, 6 plus 3 plus 4. I actually don't know. It's a very complicated paper. The point I'm trying to make here out of this is that even just the linear order, you have 9 free parameters to fit with luminosity distance data, meaning that you will never get a good fit, because we know, for example, that Pantheon Plus supernovae are barely able to fit this free, with a lot of degeneracies. No, you just have H naught. Yeah. So yeah, it's very complicated to fit with real data, this type of expansion. The hope is that one day when we will have enough data, we will be able to fully reconstruct the luminosity distance. The other way in which you can cheat, actually I'm going to show it in a second. For the moment, let's just say that this type of decomposition exists. And the other approach I was mentioning beyond cosmography is to make some symmetry assumptions, for example, spherical chaos. This is one example from a work that I did with both my supervisor, PhD supervisor, and master supervisor, when I was already not a student of them anymore. It's a model of an isotropic but homogeneous collapse based on Bianchi 9. I mentioned the Bianchi cosmologies before. Bianchi 9 is the most general anisotropic space-time that have collapse, that has closed curvature. And I use this Bianchi-9 to describe the modification, anisotropy modification of the spherical collapse. So this is how a Bianchi-9 space-time behave. It collapses in very different epoch in different directions, and the free scale factors change role all the time. And what you can get is that doing, I didn't do those were done after my paper by another group of scientists in Poland. They did numerical simulation of this Bianchi-9 and found out that actually this provide a perfect way to produce filaments. So if your question is how do filaments behave, because I can explain that very quickly. We have two analytical models of collapse. One is the spherical collapse that I did yesterday. The other one is the Zeldovich approximation, which is Friedman. So your metric is minus dt squared plus a squared. Now, the x-axis will have a perturbation lambda, but y and z not. So this is called Zeldovich approximation or Zeldovich solution. And if you do this, you get the asymptotic evolution of lambda is lambda 2 goes to 1, which means that you start with something that is basically Friedman, and then it collapses to a pancake. And this is how pancake or sheets are formed in the cosmic web. So we have a recipe, which is the spherical collapse for spherical halo, a recipe for pancake. How do we describe everything in between? Filaments. This paper was an attempt to try to answer that using Bianchi-9, and actually numerical simulation seems to confirm that this can produce filaments. And also, at the time, I didn't bother with matching conditions between Bianchi-9 and Friedman, but those authors did, and they showed that it's actually possible to do the matching using Israeli junction conditions. So this was one example of exact solution that can describe what happens if you try to match something that is not homogeneous and isotropic in a homogeneous and isotropic background. Another solution that instead is very, very old, from the 50s, is the McVitie metric. This is a beautiful, beautiful attempt. It has been, basically, if you look at this shape of the metric, it's not really clear. But if you take two asymptotic limits, which are r to infinity and a equals to 1, you get that for r equals to infinity, this matrix becomes Friedman-Robinson-Walker. As you can see, mu goes to 0 for r that goes to infinity. So you just have 1 c squared and 1 a squared dr squared with the curvature. So this becomes Friedman in the infinite limit, and if you take a equals 1, this is Schwarzschild. So you have a metric that describes a black hole, a universe which is composed of a black hole and an expanding Friedman-Robinson-Walker background. That's it. It's called McVitie metric. I've used it with two collaborators of mine to study how the shadow of a black hole changes in an expanding universe. So basically, we try to do some redshift drift out of black hole shadows. We get some constraint on the equivalence principle, which are, of course, extremely weak. There are some problems with this metric. It has been computed by McVitie assuming chemical constant, and that dust, so the Friedman part, has a perfect fluid. However, the specific shape of the Einstein tensor implies that there is some anisotropic stress, so it cannot be a perfect fluid. And if you try to solve this problem by saying that m is a function of time, you get some violation of energy conditions. So this metric is not really good. It's good only in these two asymptotic limits, which is why you can still use it to describe, black hole shadows in an expanding universe, as has been done by a few people in the literature, not just me. But in general, it's a very pathological metric. Another way of dealing with spherical spacetimes is the LTB metric, Lemaitre-Tolman-Bondi. This is a fully inhomogeneous and anisotropic metric, but spherically symmetric. And you have two scale factors, one for the radial part, one for the angular part. So basically, the universe expands in a certain way on the radial part, but also spheres between them have a different expansion rate in the angles. In this sense, it's inhomogeneous, and it also, the rate of expansion depends on the distance from the center. So this describes a void or a clustering region, if you want, that extends to infinity. You can write it in such a way that at some point it becomes Friedmann-Robinson-Walker, exactly. And you can do that because this k here and this m here are actually free functions of the solution of the full Einstein equations. So you can do whatever you want with those, including embedding them in Friedmann-Robinson-Walker. It has been studied, it's probably the most inhomogeneous spacetime studied so far. These plots were made by Valerio Marra and collaborators. Valerio is Tiufes, Thiago Castro also contributed to this paper. And this is just to show how such a void will look like in lambda LTB, so a universe which has cosmological constant is Friedmann beyond a certain radius, but is void in the center. And you get this type of deviation from large-scale structures and this type of peculiar flows. So they tested it with data, and they tried to see how much a local void is compatible with lambda CDM. And according to their combination of analysis, which includes CMB and supernovae, they found that basically it's completely allowed, or at least within 2 sigma, from the Copernican prior. So just the fluctuations of Friedmann-Robinson work described by lambda CDM. So no special void, nothing particularly weird here. Perturbation theory seems to do the job very well. And also, they try to see if this could solve the Hubble tension, and the answer is no. So, yeah, basically just variance of perturbed Friedmann-Robinson Walker. Another approach, if you want to relax the assumption of spherical symmetry, is the Chequers model. Particularly, you can think of the quasi-spherical Chequers model, which is described by like LTB, but in addition to LTB, you have a dipole term. And so these variable radii are not concentrical. And yeah, rather than having just one free function, now you have 2. And one describe this axisymmetric deviation. And as a matter of fact, you can imagine taking one Schedzeres model, try to cut a pizza slice, and another Schedzeres model, and try to cut another pizza slice, and then impose boundary condition matching this side with this side, and put together a lot of different Schedzeres solutions. This is called multi-Schedzeres model, and this is what it looks like. And you can actually use it to describe large-scale structure. Like this is one of such a sample. You can have as many filaments as you want in this pizza slice and in this pizza slice. Okay, so these approaches, I show them analytically what happens when you include data, which is why they don't look as nice as before. Cosmography is non-feasible. Basically, this convergence of the luminosity distance and the number of parameters makes everything unconstrained. So you can try to use as many data as you want. You cannot even constrain the shear at any redshift. This is kind of an example of what you could get for quadrupole, but in order to get this plot, you have to fix the direction. So you can fit the amplitude of the quadrupole, but not the direction. And to fit this direction of the quadrupole, they used galaxies, essentially. They measure the quadrupole in the galaxy distribution and plug it in. You can try to do the same place, the same game, rather than galaxies with Pantheon Plus. And again, if you leave everything free, you don't constrain nothing. But if you fix the direction, so this θ1 and θ2, you can actually constrain lambda 1 and lambda 2. So yeah, if you do this, actually you get something like the quadrupole is a relevant effect. And yeah, a nice thing is that to fix the quadrupole, they use this sample of galaxies, which is from two authors which have exactly the same surname apart from one letter. Yeah. Yes, they are trying to constrain the amplitude on the quadrupole in Pantheon Plus, fixing the direction of the quadrupole to these galaxies. Yeah, so the direction is this θ1 and θ2, so they fix these two angles using these galaxies. That if you don't use this galaxy, it's everything unconstrained. So, yeah. And they also find a dipole, which is this one. Well, by eye, if those are standard galactic coordinates, yes, it is compatible with the CMB1 in terms of direction. In terms of amplitude, they found that both the quadrupole and the monopole are significantly of the same amplitude as the dipole of the bulk velocity. Exactly. From this one, yes. And actually, it might have also a contribution from the quadrupole. All of this is just to say, according to what I understood from this paper, at the moment, you cannot constrain everything, but if you just think about the amplitude of the quadrupole you see in supernova data, it is not negligible. There is a quadrupole, and this is compatible with what you expect in terms of amplitude from a dipole that is due to your velocity. So yeah, this is just to make a list of attempts of measuring these sort of cosmographic parameters using real data. That's everything that I want you to see with those slides. It has been done also for velocities using Tully-Fisher and basically Cosmic Flow 4. It has been done by these authors using I don't know which data. Overall, you find this type of terms locally, a lot of variance in H0. But my 2 cents concerning this stuff is that really you don't have enough data or enough precision to fully constrain everything. And so the only thing you can do is to combine the two approaches using some sort of description for your first moment in the luminosity distance or whatever, but you also have to include some symmetry assumption. And I've done that. And I also say that peculiar velocities probably are the cleanest cosmological probe to do this type of stuff because they are fully degenerate with H. Which means that actually you cannot distinguish between a peculiar velocity or a differential space-dependent tuple expansion. So I use exactly this formula here to try to, with some assumptions, symmetry assumption on the space dependence on H, to measure some local quadrupole. And to do so, I reckon we should use proper definition of large-scale structures. These are available using the so-called basins of abstraction. So you measure your velocity field, you integrate it, and you build this interesting object called streamline. A region where the streamline cannot escape, it's called basin of attraction. And it's basically, if you remove the cosmological expansion, everything in that region will stay in that region. And that's the definition of large-scale structure. So it's the volume including all streamlines that cannot go out. And I applied it to our home in the cosmos, Laniakea, with these beautiful people. Laniakea is the host of the Milky Way, the super cluster of galaxies in the Milky Way, which is here, and this is how it looks in 3 dimensions. Again, the longest axis is 150 megaparsec per little h. Yeah, so I decided, okay, let's take this object here and describe it as a ellipsoid, a free actually expanding ellipsoid, so an almost spherical cow. And I said that there are no peculiar velocities, so every motion inside this ellipsoid is due to the differential rate of expansion. And all this egg, all this ellipsoid is moving with a constant pulse flow velocity with respect to the CMB. So basically, I'm describing the metric of the space-time of the local universe as being some Bianchi-1 ellipsoid inside, and then Friedmann-Robinson-Walker outside. And so this is what I did. I approximated this object with an ellipsoid, and then I fitted the data, which are peculiar velocity with respect to the center, to a free axially expanding model. These are the constraints I get from the free rate of expansion. And these are the residuals, and you can see they are all within free sigmas and almost Gaussian. So this is actually a good model, to my surprise. It's also reasonably homogeneous, because I did the same exercises by taking random points inside and recomputing DHA, HPHC, and this is the distribution of the residual. So it's almost homogeneous, apart from some structure which are reflected by this deviation from homogeneity. And then finally, try to answer the question, are these anisotropies important for the evolution of the object? And you take two cases, one in which you neglect those and say it's fully spherical, so you have just one void or one cluster, and you get this delta H with a chi-square, which is not even too bad, and this is fully compatible with the void found, for example, using LTB. But then if you add the anisotropies on top of it, you actually get a very different result, because you move from an expanding void to a collapsing object, if you include the anisotropies. And the fit is incredibly better. And this, by the way, compatible with what has been found, for example, using the quadrupole in the supernova data from Sorrenti, despite being completely different data. And yeah, so the triaxial model is extremely favored with respect to the spherical one. And you would include a positive value of delta H rather than a negative one. This is how a homogeneous distribution of sources will look in the sky, as seen from the Earth, because it's inside Laniakea. And these directions here are the quadrupole observed, for example, from galaxies, or I don't remember what data are with this one. And you get that cosmological distance get this 2% correction. And if you apply these corrections to Pantheon Plus, which are the supernova in this plot or in this animation here, you get that most of the corrections are below 1%, but there is a non-negligible amount of the sample that is like 5% of it that has 2% corrections. I'm sorry for the 0.01 should be 1, it should be 5%. So the closer the source, as you can see, bigger dots have stronger corrections. And if you redo the fit for each knot using Pantheon Plus and this correction, you get a shift of the inch-out of 0.5 kilometers per second, which is not clearly, first of all, will not be enough to solve the tension, and also is in the wrong direction to solve the tension. So this makes the tension slightly worse, but is larger than most of the systematical do it, for example, to the trip formula in supernova analysis. So if you want to do high precision cosmology, this seems to suggest that you have to really take seriously the local environment contribution to the expansion rate. Okay, preliminary result, I'm doing the same type of analysis for Chequers, this pizza slice method that I was mentioning before, and this is how the local expansion rate changes. So you can see a dipole. This is the Jacobian, so this is how much different cells in the volume change, but this is preliminary result, so I'm not spending too much time on it. Just say that if you do the same for Pantheon Plus, you will get a map of these sides, and this is how your Hubble diagram change. So I'm finally finishing. My summary is the following. Cosmology is, high precision cosmology stage, but we have a lot of evidence that the lambda CDM model might not be anymore the favorite description of the universe. In order to do really high precision cosmology, though, we need to understand what is the bias due to the local expansion rate or the presence of structures around us. And we have some options, which is cosmography, which are Excel solutions, or a combination of the two. In my humble opinion, basin of attraction are the best definition we have of last case structures, so we should use them, like I tried to tell you. And we need to use relativistic modeling in order to really assess the impact of this stuff. And that's me. Thank you. Yeah, okay, I'm on the job market, not anymore, but feel free to contact me if you want to work together with me.
So all of these effects, I guess, are stronger, no, for nearby sources, not for modern redshift.
Precisely.
If you look at beyond redshift 1,
Nothing, absolutely no correction.
then you can use, no, a different kind of probe at a large redshift, sort of to fix the back, some sort of
Background.
background values, and then
Yep.
see the discrepancy with the local physics. And
Yes.
basically, you could ascribing the discrepancy to only local structures, you could fit the parameter of the local structure.
Sure. The point is, which cosmological probe do we have both at large redshift and nearby us that we can confidently test in the same way? This must be like very small redshift, as you can see here. So supernova do the job if you trust the calibration, and that's why we can use supernova indeed. But I don't have real clues of what you can use at target redshift.
Gravitational wave, we should see. The problem is that below 100 megaparsec, it's hard to collect.
Yeah, there's not enough events. But potentially, even slightly, these are, again, correction on the distances goes as this delta chi over chi, and chi is the actual distance to the source, whereas this delta chi is the distance to the edge of Laniakea. Which means that even beyond, you get, like this is going to be roughly for the 2%, but then it can get to 1% a bit outside. So if you see some kind of quadrupolar distribution like this in, for example, gravitational wave, that could be a hint that there is something due to our local environment. But again, this is still a very rude approximation because I'm saying the universe is just background and then this egg in the middle where we live, a bit of center from the center of the egg. And that's why with this other model, I'm actually trying to keep into account of the fact that this is a void and that there is another cluster here. So fully considering the whole web of structures in the nearby universe. Which this model can see, and indeed is seeing it here. You basically have here the supercluster Shuffley, and this is the cold spot of the CMV, and you have a net gradient in delta H between the two. Whereas from Laniakea, you will just see the quadruple. Thank you.